first talk is about optical testing, and it's uncensored. I hope there's some uncensored pictures in there.
There are a few.
Oh, good. And Mike is a full-time now professional mirror maker, large mirror maker, fast focal ratios, incredible optics from what I've seen. What you've brought down to the Winter Star Party is absolutely incredible. Originally, you were an electrical engineer, if I remember correctly. What were you doing originally?
Mostly signal processing.
Signal processing.
Yeah.
Okay. Because it wasn't really specific in your bio. And he is, I guess, your research funding has went down, and your optical making has gone up. So he's now a full-time professional optician. He's written several articles for Sky and Telescope as well as astronomy magazines. And I will
Amateur astronomy.
Amateur
astronomy. Yeah.
Okay. And without any further ado, I'll pass it over.
All right. Thanks. All right. So I've got what I lovingly refer to as the food coma slot. Usually when I give talks right after lunch. So hopefully we'll be okay on staying awake. And how's the temperature? Are we doing good?
Yeah, we're fine.
All right. So.
We can make it hotter.
Yeah. We'll get this going. I should have done that a second ago. So I'm going to talk about all different kinds of optical testing from the standpoint of hopefully someone who may not know a whole lot about optics. I'm going to try and simplify it quite a bit. And to start off with, I'll go through a bunch of different types of testing, some of the advantages and disadvantages that you may or may not have heard about. I'll throw in all my opinions and experience that I can do that are, not censored, and some other random thoughts, and probably a lot of sarcasm. I love sarcasm. We'll see. But that's actually a shot I took last night, just sitting in the driveway into the camp, just to make some friends jealous, and I got the sign in it, so it was appropriate for the opening of the talk here. So when we talk about optics, we are talking about a scale with which many of us are not familiar. If you do carpentry, you might work to about a 1/16 of an inch precision with your table saw or your chop saw, or even better, you can get down to a 32nd or even more, depending on what you're doing. Of course, wood changes dimension over time with moisture, so that sort of limits the precision with which you can work with it. If you're machining metal, typically, you're going to be working to a 1,000th or a 10,000th, and there we go. Got lots of zeros at the end there to go till we get down to the millionth spot. If you're just doing, say you want to collect a bunch of light from a star or from, say, a laser that's blasting into the upper atmosphere, the LIDAR researchers do this with different wavelengths of lasers, typically in the 300 nanometer to 400 nanometer range. And that goes up hundreds of miles into the upper atmosphere. And they want to get back as many photons as possible into a pretty small 50 micron to 100 micron diameter fiber optic. They don't care about imaging. They just want to get their light back. So for that sort of application, a mirror on the order of one wave and reasonably smooth will put all the light from that particular spot in the sky into their fiber for their experiments. They can actually get Doppler shift measurements off of these LIDAR returns and figure out the air velocity in the upper atmosphere. If you want to go to optical quality, then we end up going down to this last place, and 2/millionths of an inch is roughly a 10th wave on the actual glass. So 22 millionths of an inch is roughly a wavelength, depending on what wavelength you're working at. And beyond that, we want our optics for astronomical purposes to be fairly smooth. So on the surface, generally, if you look around a small area, you want 100th of a wave smoothness or better. So that sort of gives you an idea of the scale as we get down into the optical realm, where you're dealing with almost the dimensions of atoms and molecules. So wood expands and contracts. Metal also does as well, but it's much stronger and can handle the machining forces that tools put on it. So it can be machined to a tighter tolerance than wood. And glass, again, moves on down into even a higher tolerance for being able to retain its shape. That's why we use glass for mirrors. Metal is used in some applications, but it expands and contracts more. It can change shape. And the anneal quality of metal for high quality machining as well as the glass for high quality telescopes is of the utmost importance, because what's the use if we polish a mirror to 100th wave and then it changes shape on us? That's bad. So we want to make sure there's very little strain, which strain you can sort of imagine as a spring within the glass. And if something happens, that spring can release its strain and change the shape of the material. So the other thing to mention for glass is we want to make sure that it's ready to be supported for optical work. We have to think about how we hold it. You know, if you're machining a piece of metal, in a lathe, you chuck it in there, you crank down the chuck really tight, and you start spinning it. For glass, we can't do that because it'll bend, and it'll bend more than we can accept for the optical tolerances. So generally, you want to make sure that the back of the optic or the back of the glass that you're working on is flat or is some shape that can be supported evenly so it doesn't bend during the work itself.
Isn't the modulus of glass the same as aluminum?
I don't know. But the amount of bending that's acceptable is less. He asked if the modulus of aluminum was about the same as glass, and I actually don't know the mechanical parameters off the top of my head. But it's pretty easy to bend aluminum or glass one wave, and bending glass is far worse. So I'm going to talk about strain testing first of all. This is the very first thing you want to look at. You do not want to make a mirror out of bad glass. So what we do is we pass what's called linearly polarized light, and you can get a sheet of linear polarizing material which sort of aligns the fields of the light waves or photons, whatever you'd like to call them, that are going through the glass. And then, so this is before the glass. Light goes through the polarizer, through the glass, and if there's any strain within the glass, that will change and rotate the polarization of that light. And then you put another polarizer in front of it and turn that 90 degrees to the first one. So what you end up seeing as the polarized light comes through the glass and through the two polarizers is something, hopefully, that looks like this. Now, we have, on the back of the mirror, we have what's left of a giant blob of adhesive here. We have some swirl patterns from the actual machining of the back flat. But generally, the illumination of this glass is pretty evenly gray, roughly. We don't see any bright or dark parts jumping out. So the anneal of this glass is quite good. This is something that generally can only be done with a coating off of the mirror. So whenever I do a refigure job or whenever I buy glass, I check the anneal of it right off the bat to make sure I'm not working with a bunch of springs internally in the glass. So if you want to talk about the actual precision, it's talked about in millimicrons per centimeter. So it's basically microns of effective path length change per centimeter of glass that it goes through. For those of you that are really technical, I'll just mention that. Here's a decent strain test. Now you see we start to have these light areas out here, and we have this four-sided symmetry. You know, this region is almost a diamond or a square shape, and this is pretty typical of strained glass. You see these two axes of strain, and since the polarizers rotated 90 degrees, some of that has to do with how the test is set up. So in this case, this is not bad. This made a fine mirror, and I didn't worry about the strain too much. But we'll show some worse ones here. Now this is an example of some non-American glass and actually non-European glass. Let's just say it probably came from China. We have some features in here. Anybody, what does this look like to you guys? Just out of curiosity. What's that? Striate, or possibly, it almost looks like you can see how the glass was poured into the mold. That's what it screams out to me. So this area shows some light and dark variations. They're sort of irregular. They're on one side of the mirror. So I had a little bit of reluctance to work on this mirror. I told the owner, you know, I can't guarantee it's going to stay this shape forever, but I can definitely refigure the glass, and I think it'll be pretty darn good. And it turned out he was extremely satisfied with the mirror, because it's fairly thick. The other thing you have to think about is the thicker the glass, the more of a brightness variation that is permissible, because it's measured in strain per thickness of glass, microns per centimeter. So this one stayed, and to this day, a year or so later, is still performing admirably. I think this was a 14-inch blank. Then we go on to something like this that starts to give me serious pause when it comes to working on it. We get very light, very dark, and it's got this four-sided symmetry. We're starting to form that dreaded cross that people talk about for very strained glass. Now typically this stuff, what you'll see a lot of times is as the mirror cools, you'll see astigmatism in the images. That's one telltale sign, but it'll go away as the mirror cools off, and it will rotate with the mirror, but it just goes away as the night goes on and as you get equilibrated. So it's another sort of false astigmatism that's not actually in the figure. Now it can be polished in because during polishing, the heat will warm up the glass and actually cause it to warp, asymmetrically. So there's a lot of possibilities here, and sometimes it's hard to tease out. Now we have some quite bad mirrors. This is rotating the polarizer. This is probably actually, we call it the cross polarizer test because we have one going this way and one going this way. But just to show how bad this mirror was, I put them the same direction. So this is just one direction of polarized light going through the mirror. And when you see that without turning the other polarizer, you got to say, oh no, here we go. And rotated 45 degrees or so, we see this, and at 90 degrees, we see that. And that is not something that you want to work on. It will produce probably an astigmatic mirror, and it will do weird things over the course of the night. It would definitely want to be re-annealed. Annealing, by the way, is heating up the glass to a particular temperature called the anneal point. You hold there for a short period of time, and then you slowly lower the temperature, on the order of a degree or two per hour, depending on the annealing schedule of the material. So that's how you fix it. Of course, when you do that, the shape of the mirror changes, and anything you polished in is trashed, and you need to regrind and repolish the mirror. This is a bigger blank with really bizarre, stronger, multiple bullseye patterns of strain and did not polish out to a figure of revolution, and I had to reject it. This is an interesting little piece of glass that I don't know where it came from, but I use this as my official strain demonstrator for Lockwood Custom Optics because it's got these cool colors out here in this funky pattern. It's about 1 inch thick. It sort of looks like plate glass. I'm not sure exactly what it is, but if you worked on it, it might just break on you if you start grinding it. Or if you send it through a large temperature shock, throw it in some cold water, it might break. I don't know. This brings me to another slide. If you want to actually do some strain testing, we have a wonderful resource nowadays. We have all these LCD screens on your iPad, your phone, your TV. They're all polarized light. So if you put a white image on the screen, you have your first set of linearly polarized light. Then all you need in front of that, or in front of your eye or your camera, is a small piece of linear polarizer. You rotate it and you watch for brightness variations. If you have an uncoated mirror, you can do strain testing with your TV or with your iPad here. So here's the iPad with a little white image on it, and that's the same blank as the previous slide. So now that we have a piece of glass, that hopefully doesn't have any strain in it or no significant strain, then we want to look at how do we prepare this piece of glass for high precision optical work. And this slide really tells you, and it kind of shows you graphically what you have to watch out for. So this is a blank that is just beginning to be ground on the back. So I have some newspaper underneath it here. Here are the 3 things that keep it on the mirror turntable. And you notice I had drawn a grid of marker lines, sort of like this, like a checkerboard pattern on here. And you can still see some of them right here. So what does that tell you? This area was high. It wasn't flat, right? And it's not flat yet. So I need to continue grinding the back of this mirror down to whatever abrasive I choose, typically 5 to 12 micron, in order to make the back of this mirror flat. Otherwise, when you press on this mirror with any pressure when you're polishing, this part will bend down more than this part will, and you'll end up with an astigmatic blank. Now the same, of course, goes for whatever's underneath the mirror. The turntable needs to be quite flat I try to get it down to, thousandths of an inch. And you also put a squishy layer between the turntable and the mirror. And you typically will rotate the mirror to different angles as you do the work, so that if there is a little bit of curving due to the polishing pressure, then it's sort of randomly distributed. And generally that will keep you from grinding any astigmatism into the mirror. And if you also do it right, polishing a piece of glass with low strain in it, you will get generally a good figure of revolution. Generally, unless something goes wrong, which it happens occasionally, and then you have to figure out what it was and fix it. So a figure of revolution, is if you slice a mirror across any diameter, so if you slice it this way or this way, and you look at the curve and you measured it, it would be the same. If you have astigmatism, the curve might be slightly shallower on one axis than the other, And there are other higher order, we call them aberrations, that mean that you may have a high bump here, and high bump here, and low bumps in between them. If it's 3 of those, that's a form of trefoil. It's an optical aberration. So you can have all kinds of weird shapes. And often, the actual reason for this right here is because it was annealed, and it changed shape as it was annealed after it was machined. So you have to go back and regrind and make things flat again because the strain released, the blank changed shape, and you have to watch out for that. So how are we doing? Anybody got any questions off the top of their head? Everybody still awake here? We doing good? Okay. So there's a rough tolerance, maybe a 10,000th of an inch, but just depends on what you want to do. It also has the added benefit of getting rid of all those swirl marks that I showed before in some of those other images, which are fractures from the actual generation process, the machining of the glass that was done before I get it. And it makes the back of the mirror nice and smooth, which makes it slide around on the back support more freely and is less likely to cause support problems. So here's a dial indicator. You can read it out here. It's got 5 digits, and the last one's either a 5 or a 0. So we can get down to a 20,000th of an inch with this dial indicator. A couple waves, or a few waves. Just depends on how you do it. The larger the spherometer base, there are little ball bearings under here. There are 3 of them. With this device, you can measure the radius of a mirror down to about a radius of curvature down to about a 1/4 of an inch. So you can control your focal length to roughly half that if things go right. I usually shoot for a 1/4 inch of focal length tolerance as a really tight tolerance. This measures, 1 point at a time. And so you can't really figure out, is the surface uneven? All you can do is get a general idea of the curve. You have to rely on the mechanical process of grinding and polishing to actually create an even curve. So now we grind the mirror, we polish the mirror, and we start talking about optical means of testing, where you actually bounce light off the mirror and it comes back and you analyze it. So you have a source, and then you have an analysis method. And the diagram here, ROC stands for radius of curvature. So if you put a source here, and let's say we have a spherical mirror, the light from this source, which is tiny, goes out, hits the mirror, and comes back and forms an image of that source. In theory, just about the same size if it's a good spherical mirror, at a point that's either at the same point or just a little bit shifted. Now, if you shift it a little bit, you introduce a little bit of astigmatism in the measurement itself. That's due to the test setup, but normally we can ignore that. There are also lots of test devices where the source and the analyzer are right on top of each other. Typically, interferometers do it that way. So there shouldn't be any introduced astigmatism due to the test setup itself. Now, Foucault testing with a knife edge does have a little bit inherently in it, and I'll talk about more of that later on. So the light goes out, gets reflected, and comes back. And we can either put a knife edge here or something else. And just if you don't understand radius of curvature, imagine that you put one end of a string here and one end here. And if you swing that string, it will perfectly trace out the surface of that mirror. So that's actually the radius of part of a circle. This would be a giant circle going all the way around here. And that mirror is just a portion of it. So to test that concave mirror or flat mirror is generally the simplest. Testing convex mirrors adds another level of complexity. I'm not really going to go into that in this talk. You can use somewhat similar techniques. That's another talk. And you need auxiliary optics. So you can also have off-axis mirrors, which are, let's say, a portion of that mirror. If you cut out, let's say, this part of it, that's an off-axis mirror because it doesn't include the actual optical axis, which is the line right through the center of the mirror here. And, of course, fabrication costs for something like that go up because it's a lot trickier to make. So this is a slide that really, for a lot of people, helps them understand what's going on with optical testing, if you think about it for a minute. So we have, this is how mirror curves work and how the geometry works without going through the math. So we have an image, and we have a tiny, tiny, tiny source right here. It can either be a pinhole illuminated by a very bright light. It could be the focus of an interferometer. It could be actually a knife edge, the image of the slit, if we allow it to be a little bit taller but still quite narrow along one axis. and it goes out and hits that spherical mirror and it comes back exactly to the same place. Any questions on that? That's how a sphere works. And that's the basis of a lot of optical testing. Now, if we take what's called an ellipsoid. So for clarity, if you have a Newtonian telescope, your mirror is somewhere close to a paraboloid. A spherical mirror is typically where we start when we're figuring one of those. And in between, all shapes in between are ellipsoids. So the properties of an ellipsoid are if you have a source here, it makes a perfect image of the source here. So if you have a tree 30 feet away from your telescope, if you have the right elliptical shape on the mirror, you will get a perfect image of a small part of that tree at this spot. Okay? So we go on up to a paraboloid. Now if we have light from infinite distance away, starlight, which is parallel, coming in here, it forms a perfect image right here at the focal length of a star, a tiny, tiny source out at infinity. So those are the properties of the different shapes. Any questions on those? Okay, so if you want a perfect telescope for a finite distance, you need an ellipsoid mirror, not a parabola. And that is a lot of the foundation right there of optical testing, because that allows us to go into other types of tests. So I call this the tiny, tiny source test. You might call this an artificial star test. Also, this is the focus of an interferometer can be considered a tiny, tiny source. And you can look at the return of that image from a spherical mirror, and ideally it's going to look like this. It's going to have a central spot, it's going to have rings, and it's going to be round. So this is a good artificial star test of a spherical mirror. Like I might typically do in testing a mirror cell. I'll actually put the spherical mirror in the cell, tilt it up on edge, and test the edge support of the mirror cell, because that's a major source of problems with telescopes. So for the spherical mirror, it forms that nice image. If the mirror isn't spherical, or if it has some astigmatism or some other distortions, you start getting funny shapes here. This is a form of astigmatism, and it depends on where you focus it. But non-round images are bad, generally. And here's a really bad one. I think this was a really bad, fast 8-inch mirror that was supposed to be parabolic, but it's a bizarre shape, and it forms these strange things. And the rings out here aren't round either. So this is one test I can use along the way. Right after I polish a mirror out, I look at its figure of revolution to make sure it doesn't have any astigmatism before I start doing the figuring process of taking it from somewhere near a sphere to a parabola or to a hyperbola or to an ellipse, depending on what the telescope requires. These photos are basically down here are a non-null test, because all the light isn't coming to a focus at a point. It is focusing on a portion of a mirror at the time, and I'll talk about that more in a little bit. But you can still run through the focus and see these distortions and get an idea if you're in the right ballpark or if you've got problems. It's a kind of a quick test. So we will go on to null test arrangements. Now, null test, all that really means is you have a tiny, tiny source, and the light goes out and comes back and creates an image of that tiny, tiny source. And that is the perfect image for that system. So here we have our light source, spherical mirror, back to the testing point, just about a perfect image except for a little bit of astigmatism from being off axis. Or you can get right on axis with, this could be an interferometer diverger, which actually focuses the light, and the light goes past the focus and expands out to fill the mirror that you're testing. That's how you get a diverging beam. You actually converge it first. But there's your focus. There's your tiny, tiny source right there, going out, coming back right there, and it goes back through the system and gets analyzed by the interferometer. Getting a really fast, as in a very quickly diverging interferometer beam, gets to be quite expensive because they're very hard to make cheaply. They're impossible to make cheaply. They're very expensive. So testing fast mirrors can be, that's one of the reasons they're more difficult. It's harder to get the actual components for the interferometer to do it. Another way we can look at this is we have our tiny, tiny source out here. We're going to bounce it off a flat mirror. And we're going to bounce it then off of a spherical mirror that we know is a good sphere. We can test this very accurately with the Foucault test. That's the one very simple test that will let you make an extremely high precision optic. And then build off of that into testing and improving your other reference elements in your shop. So the flat, then, if it's not flat, will impart distortions, and we'll see that in the returning image. Any questions on any of this? Anything? All right. Then we go to the famous Runkey test, which consists of putting a grating, which is a series of lines, they're often so fine they're hard to see, between a light source and the mirror. And the light can travel out through the grating and back through it, and you see the actual shadows of the lines. And for a spherical wavefront, you end up with straight lines. If it's not a spherical wavefront coming back, then you'll bend those lines. And the thing about the Runkey test is it's very difficult to do high precision work with it. It's not a very sensitive test. It'll give you an idea, is there a problem? Or what is the problem? But it's hard to actually measure the amount. That more relies on experience. So use it occasionally. You can actually put one in an eyepiece in the focuser of a telescope and do a Runkey test on a star image. And you can see if the bands bend at all. But for a quarter or a half wave of problems in a telescope, the bend is not going to be very much, and you have to work to detect it. Let's see, all right. So we're going to talk about more test arrangements here. Now this is something that I built. It's called a collimator, and it's basically a Newtonian telescope working in reverse. We have a tiny, tiny source here, which in this case for me is a laser focused on a 2 or 3 micron pinhole. Now that is just a joy to try and do, to actually find the pinhole with the focused laser light, because you can't see it. So it can sometimes take hours to get this thing set up properly. But if you have that tiny source at the focus, exact focus of this parabolic mirror, the light goes out, hits that parabolic mirror, and it makes parallel light, which is pretty much the same as starlight, but it's in your shop. It's canned starlight for your shop. And if this is an interferometer here, or you can put it right in the middle of the beam, you're just going to block some of it, and you put a flat out here, you can actually test that flat using that collimator setup. Now you've all heard of a zygo interferometer, yes? Yeah, nod. Show me you're awake. Okay. Typically that will have about a 4-inch collimated beam, and it'll be very accurate. At least the 10th wave, maybe a 20th. I built a 24-inch collimated beam, and it's not perfect, but I continue to improve it, and it lets me test very large elliptical flats without having to set them on other flats and have them bend due to gravity. We'll talk more about other flat testing later on, but this is a very advantageous way to get a good accurate test of large flat mirrors. It's not easy to do. Gravity fights you all the way because typically these things are set up horizontally with the mirror on edge. Then this is what's called an autocollimation test for a parabolic mirror. So some opticians work this way. They have a flat with a hole in it. Okay, so this is like if we cut the flat in half right here. This is the parabolic primary. The interferometer or the tester sits right here. Light goes out, hits the parabolic mirror, becomes pretty much parallel, hits the flat, comes back, and reconverges. And if both optics are perfect, we get that perfect return. So we see the error of the primary twice as much as the flat because the light in this arrangement bounces off the primary, parabolic primary, twice and off the flat once. So of course you can set this test up, and if you know you have a perfect parabolic mirror, you can work on your flat until it's perfect. Just another way to improve the accuracy of your own test equipment. This arrangement uses several bounces, and there's a hole in the parabolic primary mirror for this arrangement. Bounce, 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 parallel light, and back. And in this case, you get 3 bounces off that flat. And it's a lot more sensitive to errors on the flat. So, okay, we'll get out of the diagrams and everybody can wake up. This is something in my shop that I had set up as a rough check of a 50-inch RC system. So way back here in this holder, we have a 50-inch primary mirror, f2.2 hyperbola. It's finished. In this holder here is its 14 3/4-inch secondary mirror, which I'm still working on. That system had problems with all the mirrors. And this is my collimator sitting right here. This is the back of the 24-inch mirror, so I was aiming parallel light at this system and sort of observing the return to see, is this complete crap or is this only somewhat crap? And it turns out it was somewhat crap. And then so later on you go set up another arrangement with a flattened interferometer and you can actually see the high areas you need to remove. This was a quick Runkey test through that system, so you can see the lines are not too bent, but there is somewhat of a mess going on. And this image is a mess just due to the diffraction of the grating. Now we're going to jump to Foucault testing. Has anyone done Foucault testing? Jump up and down, wave your hands. Okay. This is what I use for most of my work because all we have in the system is a source and a knife edge or a straight edge. That's it. You measure the position of this source as it moves away and toward the mirror, and by doing that, you can actually figure out what the slope is of different parts of the mirror. So here, we see the shadow of what would be a parabola or an ellipse, and if you reversed it, it would be an oblate spheroid for those of you that have done this. But we see that you put this knife edge in